More and more, I hear people say that algorithms are black boxes and that nobody knows how they work. There's a reason for that, and it's the deep learning bros and the people who pay them millions of dollars to make things unnecessarily opaque. Hey, I'm you from the future. You better stop what you're about to do right now. Don't you do that. If you share big tech secrets on the internet before you even know how to properly look at the camera lens, man, in the future here, we're not going to be able to get any tech sponsorships on any of our videos. Do you know how lucrative those are? No, this is important. It's widespread, and it's just getting worse. There's even a trend in academia right now where people are using neural nets and deep learning to do stuff that was previously just done with linear algebra and calculus, and then they get it published to beef up their resumes. For those who aren't in academia, publications are important. The more publications you get, the nicer jobs you get. So it's no wonder they want to do as many publications as possible. Thing is, neural nets are more complicated, complex, potentially confusing, but they're just math. According to this article by the Harvard Data Science Review, there seems to be a growing belief in data science that the most accurate models must be uninterpretable and complicated. Have you ever heard the phrase, all models are wrong, some are useful? How could we possibly know if a model's useful if we can't understand what's in it? My techie peers would probably be upset with me for sharing these tidbits, but deep learning is just squiggly line, multiple step machine learning problems, and machine learning problems are really just statistics. Seriously, it's a whole thing. If you go to a data science conference and ask a machine learning engineer what it's like to be a statistician, well, you might get punched in the face. But in reality, that's all it is. If you happen to find an old statistics book that was published before any of this stuff was widely available, like this one that I found at the Los Alamos Lab used bookstore. Most of the math that computer science students learn in machine learning class is in this book. It was published in 1965. The fundamentals of deep learning are even older. The beginning of deep learning started in about 1944. Mathematicians would just whip out their slide rule or abacus or whatever they used for math in 1944 and calculate all of this stuff. This is the same stuff that they say is in these black box algorithms that we can't interpret. I will link an article about this by Larry Hardesty from MIT in the comments. Huge companies seem to want to spring for a so-called black box deep learning algorithm so they can stamp it with the proprietary sticker. A proprietary algorithm garners them a huge valuation from investors. And then as a plus, they don't have to explain what's in the algorithm or how it works to shareholders, the regulators, the C-suite. But do uninterpretable black box algorithms actually exist? No. But also yes. Kind of. Because of tools like TensorFlow and PyTorch that allow deep learning engineers to upload data that they already have into tools that are already built. No math required. Yeah, hey there, me again. Say what you want about PyTorch, but you can't come on YouTube and talk about TensorFlow. Google created TensorFlow, and in case you didn't realize this, Google also owns YouTube, which is the platform you're trying to record this video on right now. What are you trying to do, get Google to delete our channel so that I don't exist? Maybe. Well, the tools themselves are fine. They were created by Facebook and Google to allow people a space where they can build stuff on top of the framework that's already there. The problem is that people use these tools to make algorithms opaque, either purposely or accidentally. This wouldn't be as easily done if they had to build the whole neural net from scratch. Google, of course, is an ethical company deeply concerned with social justice. They would never purposely aid in the creation of an AI dystopia. They're just trying to make it easier for deep learning engineers to avoid the one thing that scares them the most: math! Are deep learning engineers afraid of math or just self-entitled? Let's talk about why data science, machine learning, and deep learning are not black boxes, and how we know what models will be useful for what stuff. Now, I realize that this video is about to get really math and terminology heavy. I'm going to try my best to spruce it up and make it interesting, but you're the one that clicked on a video about algorithms, and there's only so much that I can do. So there are several different types of algorithms. You have supervised, unsupervised, and reinforcement machine learning algorithms. And deep learning, you have neural networks. When people talk about algorithms being a black box, I imagine they're probably talking about either the unsupervised machine learning algorithms or the deep learning neural networks. Let's go into those a little bit. While supervised machine learning algorithms are trained by humans to do a thing, usually by taking 20 to 30% of the data to train it, and then the rest, the remaining 70 to 80% to run the test, unsupervised machine learning algorithms are completely hands-off by the human. The computer decides how to group or cluster the data, and then tells you what it decided later. This may sound like a black box, but it's not. It's just based off of math. The data scientist will tell the computer should use Euclidean distance, Manhattan distance, or some other kind of distance to determine where these clusters belong in the thing. Neural networks, however, are a little bit more complicated. Neural networks use nodes that back when they were first invented, they thought resembled the human brain. These nodes are all linear regression models. Linear regression is math. These nodes are then weighted, also math, and then a supervised machine learning algorithm is trained to finish the algorithm using gradient descent, which is multivariable calculus. Math. Okay, if I keep going on this trajectory, this video is about to get either very boring or very spicy. Let me change it up. Oh, okay, I see. I'm the one that gets to explain everything, huh? Well, at least you cleaned the board for me, I guess. So with clustering, you consider each observation as a member of an n-dimensional space, where n is the number of columns. Then you calculate the distance between that point and another point in that n-dimensional space. We'll make up an example. We will make, let's say, a 10 by 3. That'll be easy-ish. Anyway, so with these points, what you do is you calculate mathematically the distance between each point. And the smaller the distance between those points, the more similar they are. And the things that have the most similarity then are grouped into the same cluster. So let's give an example, a 10 by 3. 10 observations and 3 variables. So these are just arbitrary things. I'm making up a problem. I guess I should have picked something that applied to something, but I don't have something ready. I'm putting up numbers that are the variables corresponding with that observation. So here we go. Okay, so if you want to follow along, you can take a second to pause and screenshot this so that you have the information. Okay, screenshot captured. Perfect. All right, so now what we do with this is we pick a distance. Let's just pick Euclidean. It's everything that we've already learned in school. It's the easiest to understand. Okay, so now what you're going to do is basically we're going to make what is called a distance matrix. What is a distance matrix? I'm going to write down some properties for you. So the diagonal elements all equal 0. It's like saying the distance from a point to itself is 0, okay? With a data set with n observations, aka this one, we're going to get a distance matrix that is n by n. It's going to be square. They're always going to be square. Like I said, they're always symmetric. But in specific, it's going to be symmetric in this way. Capital I, because it's the identity matrix, right? Alright, let me erase the board. Okay, so if I write out every single step of this problem, it's probably going to take 10 hours. So what I'm going to do is do one step, show you how to do it, and then you can do the rest. We're going off points 1 and 2, alright? I'm putting this dot just to signify that it's not 12. The answer to this is 0.67. I'll leave it to you to finish it. Here's the answer. Yeah, I do my math in pen. What up? The next step, after normalizing it, which we're not going to do, what you do is you select a linkage method. Now with k-means clustering, we always use a centroid. You can just substitute out the word centroid and call it average or mean. It's basically just the distance between two clusters of things. So you might have like this, okay, and this. That right there is the distance. We might have the centroid right here. This might be the mean. Now, sometimes if you want to get really fancy for business problems or other things, they might actually give you something that's other than the mean, like a benchmark or something that they're looking for. But for the case of this problem, we're just going to use the mean. And so we're looking for this distance between this and every single point. So you're going to get slightly different values, but they're all going to be relatively similar between this centroid and the points here, and between this centroid, the same centroid, and the points up here. So we can write that all out like that. Now we're going to use the variable d. This is just distance. And cm and cn are clusters. Now let's look at a deep learning neural net. Oops, how did that get there? Here's neural net math. Okay, let me erase the board. All right, we'll talk about a specific data set this time. I came prepared. Basically, it is grayscale images of integers, just digits 0 to 9. The problem, it's used in a lot of machine learning classes. The student is supposed to be able to write an algorithm that can then be used to determine what digit that is. But we're going to do it by hand. This is the name of the data set if you want to look it up and download it and try it yourself. So they're 28 by 28 pixels each. So that is 28 times 28 is 784. And each row and column are a matrix. This is computer science. We use matrices. Okay, so this is for a row. A column is just a transpose matrix of a row, so we can write that as a matrix too. In case you're wondering, I've had this question before. Math teachers write in all caps because we can only read lowercase letters when they have numbers with them, in case you're wondering. So, the events of each of these, every case, like I said, they're digits 0 to 9, and now we can use that to make a neural network. We're going to do 3 layers. So in computer science, the first layer is called the 0th layer. It's called the input layer. And then the first is the hidden layer. And the second, which is actually the third layer, is called the output layer. So the input layer here is going to have 784 nodes. And then each of the hidden layer and the output layer are both going to have 10 units each. This whole thing that we just drew, this is the neural network. There's 3 steps that we'll use to train this algorithm. The first one is called forward propagation. Let me erase the board. Okay, step 1, forward propagation. This is the input layer. Next, we will look at the hidden layer, which we're going to call Z. Now, with this, we have to have weights. So this W right here is the weight. This again is just the input layer. And this B, it helps us create kind of like a fancier linear regression type of problem. As past me said, each node is a linear regression problem.
These nodes are all linear regression models. Linear regression is math.
It kind of resembles this equation. They look the same. So as we said, this is an unactivated hidden layer. We can't use an unactivated layer, so we're going to activate it. And there are 3 different functions that are commonly used to activate it. You have sigmoid and tanh, and the last one, the one that I think is most commonly used out of all, is the ReLU. Alright, those are the 3 activation functions. We have, can you see that? X, if x is greater than 0, and it'll be 0 elsewhere. We're going to use the ReLU to activate it, and this is what we're going to get. Okay, so the A here is the activated layer 1, or the activated hidden layer. And this is what we're going to get when we apply the ReLU function. Again, you'll see that this kind of resembles a line. We're going to have to make this into, not a line. In order to do that, first step would be to use the softmax function so that we can go into step 2. Here's the softmax, and this is what it's going to look like when we put it into the equation. So you can see you take the output layer, which again is layer 2, and then you put it through the softmax, and then what you will end up with is a set of probabilities. Now let's go into backpropagation. So in backpropagation, what we're doing is we're taking the weights of each thing and we're going to test them, and then we're going to adjust the algorithm as the errors occur. So here's how we would do that mathematically. D is derivative this time. So with this activated function right here, what we're going to end up with is predictions that we're going to run through that one hop in code. This right here is the error of layer 2, and this is the prediction. So here we have the full problem. So now we can do some quick differential equations and figure out how to finish this problem. Now in this step, we're going to undo the activation function. How do you undo the activation function? You take the derivative of it, like that. Voila. Now we'll go into step 3, which is updating the parameters. So basically this is just going to look like a bunch of definitions. I'm going to use alpha here to mean the learning rate. There's our updated parameters. Now back to past me. Hopefully now you see that algorithms are nothing more than a heaping pile of math manure that data scientists shovel into a wheelbarrow and do, well, whatever people do with manure. They're interpretable and reproducible, and some people might say stinky, but it's all just math. You can put a proprietary label on it or call it a black box, but that doesn't stop somebody who knows enough math from reproducing the results. This is kind of like when biochemists patent a gene. We know what's in the gene, it's just, proteins and other biology crap, but that just means that people can't use this particular pile of biology crap for something for a certain period of time. This is like that. If you patent an algorithm, you just can't use that particular pile of stinky math manure for something for a certain period of time. So in short, algorithms are math. Math cannot be copyrighted, patented, or trademarked. However, a black box algorithm can. Now that I have probably completely and forever totally obliterated my chances of ever getting a job in deep learning, building a fancy black box proprietary algorithm for a company that wants to use it to secure a multi-million-dollar valuation from investors and pay me in stock, and then IPO, and then make me a billionaire. Let me announce the sponsor of this video. It's me! Yeah, nobody's sponsoring this controversial video, but it's an opportunity for me to announce my ethical data science and machine learning packages priced for small businesses and nonprofit organizations. Hiring somebody like me full-time usually costs about $200,000 or 1% of stock. However, buying a package from me costs about 2% of that on my website, raychipura.com. That pop was my knee.